Okay, so welcome to lecture number 5. So today we want to talk about what is called generative learning algorithms and naive Bayes. And this will be a little bit different to what we did before on logistic and linear regression. So they were quite similar because to train these models, we saw that we can, in both cases, we can use this gradient descent. But here in this case, we will see that this will work a little bit differently. So we will not have some algorithm which approaches our goal step by step. There will be just some formula in the end we can use to train our model using the training data. Okay, so where are we? So this is again the overview. Still today we are in this section here, so we still will talk about supervised learning. And this naive Bayes is one example of for classification. And also maybe next week we would do support vector machines, which will also still be in this class here. Before maybe next week we will go into this unsupervised world. Okay, so so first let's recall some notation we will use a lot today. So we will use a lot of notations from probability theory. And what we already used in the case of logistic regression was this notation here from conditional probability. So if A and B are events, then this PAB denotes the probability that event A occurs given that B occurs. Okay, so for example, A could be the event that the street is wet. This might have some probability P of A, and B, for example, could be the event that it's raining. And for example, the conditional probability that the street is wet, assuming that it's raining, it's quite high compared to maybe the probability that the street is just wet. And this we used last time in this example for logistic regression. So there we had this example of hours of studying and passing the exam. So the label was passing the exams. So this was either 0 or 1. And the feature was the hours of studying. And we wanted to describe what is the probability of passing the exam, assuming that we studied such and such hours. And so what we want to find is some function, the hypothesis h of theta, which describes the probability of passing the exam under the assumption that we studied X hours. And learning the probability of a label assuming a certain feature as an input, this type of learning is called a discriminative learning algorithm. And logistic regression is one example of this, because we tried to learn this probability. So we were trying to find these weights, these thetas, to describe this function h theta, which in this example was this logistic function of theta transpose times x. And this theta were some numbers, theta 0 up to theta d, which we, for example, obtained by doing this gradient ascent. But so this is what we did before. But what we want to do today is this generative learning algorithm. So instead of learning the probability y under the condition a given x, we want to learn x given y and the probability of y. So in this example, instead of learning the probability, what is the probability of passing the exam given a certain amount of hours studying, this would mean here we want to learn the probability, or we want to learn what is the probability of a given hours of studying, assuming we passed or we failed the exam, and the probability of, in general, what is the probability of passing an exam. So I hope the difference here is clear between these probabilities and this probability here. But now you might ask, um, I mean, in this example here with this studying and failing and passing the exam, why would we want to learn this? Because in reality, after training our machine, we still want to predict what is the probability of passing or failing an exam after given a certain hours of studying. So this is actually what we want. So this what we learned before directly is actually what we want, because this solves our problem. But in this learning method, we will learn uh, these two probabilities. And the reason why this works is of the so-called Bayes rule. So this is a simple rule from probability, stating that the probability, the conditional probability that the event A occurs, given that B is, occurs, is given by the probability of B occurring under um, given that A occurs times the probability of A divided by the probability of B. So in this picture here, this is actually what we want. But the statement is we will not learn this directly. We will learn this probability, but we will see then, therefore, we can calculate this probability, which is then on this side. And this here will give us the input for this side. So after learning these probabilities, we will use Bayes' rule to actually get what we want. Okay. But before we do this, I want to say a few words on this rule here. So I don't know if some of you already saw this. Maybe some did this in school, in high school, or at university. But maybe no feedback. Okay. So how can we understand this thing here? So why does this rule make sense? So this is the statement. And let's see why this is actually quite logical. So first of all, we can rewrite this. So instead of putting this probability of B here, we could also write it here. Right, and then the statement is the product of these two probabilities is the same as the product of these two probabilities. And so now let's assume I have an event A, and I have, so let's say this is the case when A occurs. So when I start, the probability that A occurs is, well, it's the probability that A occurs. And the other would be that A doesn't occur. So this here means, so sometimes people write this, or sometimes people write this for saying not A. So this would be either 1 minus PA or P of not A. And so here at this position, A occurred, and here at this position, A didn't occur. And now from this state here, what I want is that A and B, so this here means and. So what is the probability of going from A to A and B? Well, this is exactly the conditional probability that B occurs under the assumption that A occurred. So from here to here, so the probability that A and B, which we will just denote by this. So this comma here just means A and B, or probability of A and B. This we can calculate by going this path here. And going this path means we first need to take the probability of A and multiply it with the probability of B, assuming A. So this would be PA times PBA. Okay. But what we could also do, we could start thinking about, well, we could maybe first B occurs, so P of B, and then we could ask what needs to happen for A and B. Well, here we have then the probability that A occurs under the assumption of B. And then we see going this path here gives PB times PA, assuming B. And therefore, these two are the same, which is exactly this Bayes rule. Okay? But there are also other ways to understand this rule, but yeah. The point is that Bayes rule allows us to calculate a probability like this by knowing these probabilities. And if you go on the Wikipedia page, there are several examples which give a nice application of this rule. So in our case, why does this help? So the statement was, we will learn px, assuming y, and py. But what we want in the end is we want to know the probability y, assuming x, because this is what our model should learn. For example, the probability of passing, assuming a given input of ours. And so therefore, this will be given by Bayes rule by this probability, which we will learn, times, x assuming y, times the probability y, which we will also learn, divided by px. And px we don't know, but there's a simple formula. The probability that x happens is the same as x assuming y, and the probability, maybe let me rewrite this here. Yeah, hold on. Let's do it like this. So the probability that y occurred plus the probability of x under the assumption that y did not occur, and times the probability of y did not occur. Right? So the probability of x is the probability of y times the probability of x assuming y plus the probability of not y assuming not y and x. Is this formula clear? Okay. So therefore, we could plug this in here. And here we see if we learn py, then we also know p not y, and we will also learn this one here. So we can plug this in here. And therefore, if we know these two things, we will understand the right-hand side completely, and then can give a formula for the thing which we actually want to learn. Are there any questions so far? I saw we decreased from 19 to 18 instead of increasing. Okay. So and now, so this was somehow the introduction, but now this word naive, Bayes. So we will use this Bayes rule, but what is this naive here? And for this, we will do an explicit example. So one way where we can use this algorithm which we want to introduce is, for example, for a spam filter. And a spam filter is a classification problem where the feature is an email given by some text, and the label will be either it's a spam or it's not spam. So the label space will be, again, as in the logistic regression. Oh, so there's a question. Let's go back. So the question is for the significance. Why are we interested in this thing here? Um, well, we will always be interested in. Um, so, for example, in our example with this, our studied and um, pay, passed or failing an exam, um, we want to learn a prediction. If I give you hours I studied, then this algorithm should tell me after training what my probability is of failing or passing the exam. And this here is exactly the probability of passing or failing the exam under a given feature. So in our email example, what we want to know is if I look at an email, meaning I look at a feature, what is the probability that this email is spam or not spam? So we are really interested in this thing here. Given an email, what is the probability that this is a spam and not spam? So this is really why we are interested in this here. And yeah, and another question here, why can we calculate this by knowing this? So here, I mean, we will understand this probability here completely. So no matter what y is, so in our case, this y will be either 0 or y equals 1. So maybe what I should have written here is, for example, we want to learn this here, and here p y equals 1, and here instead of not y, this will be y equals 0 and py equals 0. So by learning this, I mean we will know what pxy equals 1 is, and we will also know what px y equals 0 is. So we can understand this, and we can understand this. So I hope this helps. There's another question I don't understand, or a remark. Continued in comparison to pxy. Oh, I see. No, I understand. Sorry, this belongs to the first question. Um, yeah, but I hope this is answered. So this is what we want in the end. So for example, we will learn this, but this pxy, but actually this is not what we are interested in. So for example, in this spam example, um, well, there it's hard to explain, but maybe in the study example, I don't want to know, assuming I passed the exam, what are my rough hours I studied? So I don't want to get the probability of, for example, of I studied 15 hours, assuming I failed or I passed the exam. So what I'm really interested in is this probability here. And maybe in the email example, this is clearer. I want to know what's the probability of something being spam or not spam. Okay. So now let's go to this example. So the label is spam or not spam. So really it's our y will be either 0 or 1. And the feature will be an email. But an email, we need to ask ourselves, what is this x here? So to work with something, we need to bring it into mathematical terms. And there are a lot of different ways to do this. And maybe the way we will do is maybe not the most efficient, but maybe the most easiest at the beginning. So what is an email? An email is a collection of words. And so how do I describe an email? And one way to describe an email is to say an email, let's say X is a feature, and I want to describe an email by zeros and ones. So I want to describe it as a vector. So here I want to also put it in 0 and 1. And for each word in the dictionary, I will have a place here in this vector, which sounds maybe a lot, but one can make this smaller later. But let's say here I have D features, and D in this case, so this is the number of features. And in this example, it's the number of words in, for example, an English dictionary. So for example, here, the first place could be an A, and then let's say N, and maybe at some point there's the word hello, and maybe at some point there's the word students, and then maybe at the end there's some word with Z. I don't know. What's a nice word with Z?
ZZYZX. It's tend to be the last word in dictionary.
The what?
ZZZZYZX. 2Z and Y and
This is the
ZX.
word?
Yeah,
This is
YZX. It's it's a place name in US.
okay. Yeah, this is okay.
Created to
This
be
is
the
a
last.
so thank you. So maybe A is a good first word, and this nice word is a good. So maybe an email will look like this. And now I will have entries. So for example, if you have an email with the words hello students and blah blah blah, then um, maybe at some point there's a, but let's assume not. But here maybe there's a hello, there's a students, and probably there's not this word in there. But this email, oh, there should be one. But this email can then be written as a vector in this feature space here. Okay. And we want to do it like this because also we want to interpret these numbers as some probabilities. So we will talk about some probabilities of words appearing in emails. And that's why we also choose here this 0 and 1. And maybe, even though maybe in application you would not use all words, so maybe you would just use the top 10,000, where maybe this word will not maybe be in there. Okay, so now we have our feature space and our label space. And now, so now I want to describe this naive Bayes algorithm. And for this, I want to explain what we mean by this naive. So for this algorithm, we will make a big assumption, which is called the naive Bayes assumption. And this assumption is that the features, so the different words, are what is called conditionally independent given the label. And to understand this, we need to understand what we mean by this word here. But basically what this means is that if we have an email and I tell you that this email is spam, and you know the probability that this email contains the word hello, then this doesn't change the probability that this email also contains the word student. So this means these words, given the label, so if you know that this is spam or not spam, and you know that there's a word in there, this will not influence another word. Even though this is maybe a quite strong assumption, because maybe in reality, maybe this is not true. Because if I have an email and I know it's spam, and maybe it contains what is a good example for spam? Maybe there are some words which always are contained in spam together. So let's say you get a lot of spam emails from Nagoya University, and your spam folder is full of emails from Nagoya University. then if I tell you that an email is spam and it contains the word Nagoya, then the probability that it also contains the word university is quite high. And this would mean that these features are not conditionally independent. But we will assume that this is the case. And this is a strong assumption, but in reality, it seems that this assumption is actually not bad, and this algorithm gives good results. So, so let me quote Wikipedia what it says on this word conditionally independent. So an event A and B are conditionally independent given C. So it doesn't make sense to just say A and B are conditionally independent. You always need to say given some other event. Otherwise, this notation is not defined. There's another notation which is called just independent, and you can say two events are independent. So if I roll two dices, then the outcome of these two dices are independent. But this notion here, conditionally independent, is something different. So A and B are called conditionally independent given C. If the knowledge that C occurs, for example, something is a spam, um, and the knowledge of whether A occurs, this doesn't give an additional information on the likelihood of B. So if I know email is spam and it contains the word student, then this doesn't influence the probability that this email also contains the word hello, and also the other way around. And this is an assumption we will do in the following. And then we might ask, what mathematical implication does this have? So, um, so if I have two labels, I had two features, sorry. So if I have two features which are conditionally independent, given y, um, then this means that the probability of the first one given y is the same as this given y and x. So if I know something is spam and it contains, for example, the word hello, um, then this probability that it contains the word hello and it's spam is not influenced if it also contains the word student. Therefore, these two probabilities are the same. So I don't know how clear this notation here is. So this here really means the probability of x1 given y1 and x2. So this comma here is always an and this line here is always this conditional probability. And what we want to learn is this probability here. So the probability given an feature x under the condition y. So x is our email, and this is given by this vector here. And these x I, they can be either 0 or 1. So each position corresponds to a word in the dictionary. And if at position 1000 I have the word hello, then so maybe let's say here I have a dictionary with words 1, 2, and at position 1000 I have the word hello, then x 1000 equals 1. This means x contains the word hello. Okay, so and what we want to learn is this thing here. So we want to learn given the feature x, the email, and the email means that we have all these things happen here at the same time. So for example, in our example with hello students, we have that x1 is 0, so was not there, everything is 0, and then x1000 is 1, and then maybe the x, I don't know, for the student 20,000 is 1, and then xd is 0. So this email is given by this event here, that this is 1, and the rest is 0. And we want to learn the probability of this email under the knowledge if this y is spam or not. Okay. And to calculate this, we will use this strong assumption here, and also something which is called the chain rule of probabilities, which just says that the probability that A and B occurs is the probability that B occurs and the probability that A occurs given B. And using this and this here, so we will now calculate this probability here. Okay, so here I just wrote it again. We use our assumption that all these events here are conditionally independent given y, and we will use this chain rule. And so this I will do just with one example. So let's assume the case d equals 3. So let's say we have a dictionary with 3 words, and I want to calculate this here. Then by the chain rule, this is the same as x1, x2 given y and x3 times the probability of x3 given y, where it's a little bit extension of this rule here, but so this is a chain rule. And then we use it again here, p x1 given y, x2, x3 with times x2, y, x3 times p x3 given y. So this is also, maybe use different colors. This is both given by the chain rule. But now we can assume we have our assumption here that these x's are conditionally independent given y, and therefore this probability and this probability we can rewrite. So here the probability of x1 given y is the same as the probability of x1 given y and x2 and x3. Because the probability of these two words being there or not will not influence the probability of this word appearing given this y. So therefore, under this assumption, we can write this as p x1y. And here we can also get rid of this x3 because this doesn't change the probability. And this is p x2y, and here p x3y. And therefore, in this case, it's just a product of these conditional probabilities. And in general, so I can write it like this. I think I use an I here from 1 to d p xi given y. And this works in general. So we will use this chain rule d minus 1 times, and then we use this assumption. So this probability here in the end is just the product of these probabilities. So again, when speaking about emails and spam, the probability um, that given I have an email which is spam, that this contains these words is just given by the products of the probabilities that given an email which is spam contains xi's. Okay. Are there any questions so far? Maybe it's a little bit confusing at the beginning. So again, we are, maybe let me go back to the beginning. Um, what we are doing right now is we try to calculate this guy here. Given the label, in our case, spam or not spam, what is the probability that these words are contained in this email? And then after describing this, so we now gave a formula for this, and there will also be a formula for this, giving some training data. Then in the end, we will use this rule here to get this formula for our spam filter. Okay. So now what we want to do is in the logistic regression case, we had these thetas. After getting some training data, we needed to train our model and save some data, namely this theta. And then this theta we could use to construct our hypothesis. And this hypothesis was then used to predict for new incoming data, is this passing or failing the exam in our exam example. So here we will also need, given some training data, we will need to save some weights. And in this case here, so this here is just a formula I wrote before. So this is what we did here. So this was also P x, y. This was given here, because in this example, x was x1, x2, x3. And the email was just the occurrences of these three words, or the yeah, the probability of all these three events appearing. And so the formula we derived before is just this here, because this we will use now. And now the things we want to learn, and which we then later use for our prediction, are these things here. So what we want to learn, so let me go back to the beginning. So this here is what we want to learn. And maybe it's even better to here. So we want to learn these things here. So we want to understand the probability of a word appearing under this, or an email appearing under the assumption that it's spam. And we want to know the probability of an email under the assumption it's not spam. And we want to understand this PY here, the probability that in any email is spam or not spam. And so these are the probabilities we want to understand, and this is what we want to train. And so in this slide here, I just give them names. So for each word, so this is what we want to learn, but we learned in the slide before that this probability of an email the probability of an email under the assumption that it's spam is just given by the product of these probabilities of a word, or this should be an I here. And therefore we need to know these probabilities here. And this, I just give two names here. So this phi I y1 is exactly the probability that the word xi appears under the assumption that it's spam. And phi I y equals 0 is a probability that the word appears under the assumption that this email is not spam. Yeah. So, and the phi y equals 1 is just the probability of being of of a spam. So this is what we want to save, and then later we will use this to make a prediction. And so on the next slide, I will explain how to train this. But first, assuming we know these values, so this somehow corresponds to our theta, to our old theta, which we saved and then used again. If we have new incoming data, we use these theta to make a prediction. And similar here, we will have these probabilities, and then we use them when there's a new email incoming. We will use these numbers to predict if this new email is spam or not spam. So this is what we do here. Or maybe first I should rewrite these maybe in words. So this is a probability here. So this is a probability that the word xi appears in a spam email. Oops. And this one here is a probability that this word appears in a non-spam email. Right? So for example, the word buy maybe has a higher probability to appear in a spam email. And maybe the word, I don't know, Henrik Bachmann has a quite low probability of appearing in a spam email. So therefore, this number for my name would maybe be smaller than the probability of the word buy or click this link. Well, it's not one word, but maybe the word link or buy has a higher probability. And assuming we have these numbers, now what happens if we get a new email? In other words, what happens if someone sends us an element in X? And what we want to calculate is the probability that this new X is a spam email. And if this is high, then we will put it in the spam folder. And for this, we use the Bayes rule by writing it like this here. But this we can now rewrite because we learned this probability here. This is given here. So we can write this as a product. I goes from 1 to D of these individual probabilities that a word appears in a spam email. So for example, in these cases, we have exactly the product of these numbers here. So here it's phi I y equals 1. And the probability that spam email is that y equals 1 is just this phi y equals 1 divided by px. And here we can use this. Oh, this is here's an error. Here for the denominator, we can use this formula which we discussed before. The probability of something can be written as a sum like this. So the something assuming y equals 1 times the probability of y equals 1, and the probability of the something assuming y is 0 times the probability of y equals 0. Um, so here we can take the same product here, because this part is exactly this. Oh, maybe, I mean, this is pink. And this part here is this. Plus, and now we have the probabilities that a word appears in a non-spam email, and these are given by these numbers here. So here we can take the product, I goes from 1 to d, phi I y equals 0 times. And now we have the probability that something is, that an arbitrary email is not spam, and there we can just take 1 minus phi y equals 1. Because if I know the probability of something being spam email is this probability here, then 1 minus this gives the probability of something not being spam. So the statement of this here is that if we know these numbers, which we will derive in the next slide, if we know these numbers, then if someone sends us a new email, then we can use this formula to calculate the probability that this new email is spam. And then we can decide if we will delete it or not. Okay. Other questions on these things? Not a lot of people showing their faces, but those who are, they don't seem happy. Okay. Now they are happy. Okay. So we want to calculate these things here. And so I said they correspond somehow to our theta, and the theta we needed to do some work. We needed to do this gradient ascent and or the gradient descent for this linear regression. But in this case, if we give them some training data, then these probabilities are actually quite easy to calculate. So even though it looks harder than it is, so now we want to train our algorithm, or which is also called the naive Bayes classifier. So this here will be the classifier, the spam filter. Having these weights or these parameter, we can give a prediction for a new email if it's spam or not spam. And how can we calculate these numbers? So this is just what was written on the slide before. So of course we need some training data. So we first need to have a collection of emails. So here the training data is, again, we have some emails. So these are some emails. And here we know for each of these emails if it's spam or not. So for example, if you use Google Mail, for example, there, if you have an email, there's a button, report spam. And this you can see as some training for the spam filter of Google. So every time you click this button, you give Google a new training example for their learning algorithm. So we can assume we have some set of emails and with a label if it's spam or not spam. And having this, we now want to give some formulas for these numbers. So, and for this, there's we introduce some notation here. So this is the notation I use here. Oops, the so-called indicator function, which is either 1 or 0. And this just, if I have a statement S, as is a statement. Uh, then this is either 1 or 0. For example, I of 1 plus 1 equals 3. This would be 0 because this statement is wrong. And this is just a notation we can use to write down things easier. So, but now let's try to give a formula for this thing here. So we have some training set, and now we want to give the probability that the word xi appears in a spam email. And therefore we need to look at all spam emails, and we need to count how often, in how many of these emails does the word xi appear. And then we can give an estimation for this probability, right? So therefore, this is exactly this formula here. So for a given I, so I runs now from 1 to d. And remember, d is the number of words in dictionary, or the number of features. So for each I, we can now take the sum over our training set and count the emails which are spam and which also contain this word xi. So here, each of these emails is a vector, and each vector has some entries I, and the xi of this training example j is either 0 or 1, and this says if this word is contained in this email or not. So therefore here what we count is for a given I, the number of spam emails which contain the word the xi. And then we divide it by the number of spam emails, which is just the sum over all trainings example, where the corresponding label is 1, meaning it's a spam email. So here it's really exactly this probability where we calculate the probability for a given word that it's contained in a spam email. And this probability here, so this is the probability of a word appearing in a non-spam email. It's the same formula, but for this, we just need to count the non-spam emails. And here we count the number of non-spam emails which contain this word. And then the probability that an email is spam, well, for this, we just need to count the number of spam emails and divide it by the number of all emails in our training set. So therefore, n is the number of trainings example. And here we just take the sum over all trainings example and check if this corresponding training example is spam. And therefore, this gives the probability of something being a spam email. So for example, if I have 10 trainings example and 3 of them are spam, then this here is just 30%. So the capital I is just the indicator function. So maybe we can do an explicit example. So let's do an example. So let's say we have d equals 3. So let's say we have a dictionary. Dictionary, hello, you, and there. And so now let's say I have an email. So let's do a trainings example. And the first trainings example, I have the email 101 and 0. So this trainings example means the email, hello there, is not spam. So because the y is 0 and the feature is 101, meaning I have hello in there, you I don't have, and but I have there. And let's say the second trainings example is, or maybe let's do 3 trainings examples. Maybe I should erase this. Let's say 1, 1, or let's say 100, and let's say this is spam. So just hello is spam. And maybe the email hello you there is not spam. Oops, hello you there. Okay, and now let's see how this formula here works. So how does this indicator function works? So for example, we want to calculate phi 1 y equals 1. So what was the phi 1? Maybe also copy this one here. So 1 corresponds to the word hello, and therefore this phi 1 y equals 1 is a probability that the word hello appears in a spam email. And therefore, we need to look at all spam emails and see in how many of them the word hello appears. Yes. So the formula here is, I take the sum, j goes from 1 to 3. So here in our example, n equals 3. I have 3 trainings example. And then I take I, x1 of this trainings example is 1. And the corresponding label is 1. And here I take the sum, j goes from 1 to n. And I, this is 1. So I take the sum over each of these positions here. So for j equals 1, I look at the first trainings example. And now I check the first trainings example, x1, 1, is this 1? And indeed, this is 1. So this is true. And is y, so what is y1? Is this 1? Well, in this case, this is 0. Therefore, this statement is false. And therefore, I of the statement is 0. So this doesn't give anything here. So the first summand would be 0 plus, so this is j equals 1. Because the indicator function just gives 1 if this statement here is true. So the second, j equals 2, we need to check if j21 is 1. So is this here 1? Yes. And y2 equals 1. This is 1. Therefore, this statement in the case j equals 2 is true. And therefore, we add a 1 here. Plus, and j equals 3. Is x1 1? Yes. Is y1? No. So the statement is false, and therefore the indicator function is 0. So this is 1, because the word in all the spam emails, the word hello appears once. Well, but here in this case, we just go through all of them and check if the y is 1 or not. Here it's not, here it is, and here it's not. So it's also the same. So in this case, it's 1. So the probability that if I have a spam email that it contains the word hello is 100%, because the training example here is quite small, right? So assuming I have a spam email, all of the spam emails in my trainings example contain the word hello. So that is why in this example, this probability is 1. Maybe a more interesting example would be to see what is phi 2y equals 0. So this here is a question. So 2 means I consider the word you, and I ask what is the probability of having the word you, assuming I have a non-spam email. And how many non-spam emails do I have? I have 2. But just in one of them, I have the word you. So in this case, the probability would be 1/2. And for example, what is the y? Y equals 1. So what is the probability of an email being spam? Well, in this case, I have 3 emails and one of them is spam. So in this case, the probability is 1/3. And this is how you calculate these numbers by a given trainings example. I hope this answers the question about the I. So the I is just maybe a confusing notation to write down these formulas, but it just means this sum here just means I want to go through all of these trainings examples here. And for each trainings example, I want to see if the corresponding entry is 1. And I also want to see if the second, is it spam or not spam. And this is then just either 1 or 0. And therefore, given a training set, we can calculate these numbers, and then we can save these numbers. And anytime someone sends us an email, we can use this formula to calculate the probability of this email being spam or not. Okay. Are there any questions? So, I mean, this is now the really rough version of this naive Bayes, but I hope the main idea behind this became clear. So I didn't include code today, but maybe this is something you can try by yourself to maybe make a dictionary with a few words and then create some training set and try to calculate these numbers and then write yourself an email in this dictionary and sees what your algorithm decides if this is spam or not spam. Okay. And this is basically all for today. So next time I want to talk about, so next time will be maybe longer. So there I want to talk about this support vector machines, which will be again a little bit more linear algebra and maybe also some calculus. And today was purely probability. So maybe I will stop recording and then you can scream your questions if you have some.